Hey everyone, this is Nadeem and welcome to my YouTube channel. Today we will discuss about the average and RMS value of alternating current. This is the device which is used for detection of the small current, and if we connect this probe of this galvanometer with the positive terminal of the DC supply and this probe of this galvanometer with the negative terminal of the DC supply, so the voltage or the current of this DC supply will be shown by this needle of the galvanometer, and due to that that needle is depicted here. Okay, it will be present at this position. Okay, let's say that the deflection is 10 ampere. And now what will happen if we connect this probe of these probes of the galvanometer with the AC supply? So I'm going to disconnect it, and now I'm going to connect this probe of the galvanometer with the one terminal of the AC supply and the other probe of the galvanometer with the other terminal of the AC supply. Okay, so here what will the deflection of this needle? Okay, so if we connect the AC supply, and we know that in AC supply the polarity is changing. Let's say this side become positive and this is the negative. In that case, this needle will be deflected on the right side of this zero, and here if it change its polarity, then this become negative and this is the positive. In this case this needle of the galvanometer will be detected on the left side of this zero. Okay, again this AC supply change its polarity and this side become positive, this is become negative. Again the deflection is the needle is deflected towards the right side of this zero, and if change its polarity again, then that needle will be deflected on the left side of this zero. In this way, in many countries the frequency of the alternating current is about 50 hertz. It means that here this due to the change in polarity, this needle of the galvanometer is vibrating, and the frequency of that vibration of the needle of the galvanometer is also 50 hertz. Okay, so here this is vibrating. So if this needle is vibrating in case of the DC, in case of the AC supply, okay, then it is almost impossible to say that whether the needle is present at let's say at one position, or it is present at 2 ampere, or it is present at 3 ampere, and at what value it is present at a specific interval, because it is vibrating so quickly. Okay, it do not give us a specific value. It is vibrating at each and every instant. Their magnitude and the polarity is changing. Okay, so therefore we do not say that this needle is present at a specific single point. So this is the problem here. Okay, so in case of the DC there was no problem. This needle of the galvanometer was present at a specific position. Now in case of the AC, this needle is vibrating, and we do not directly tell that this needle is present at let's say it is present at 5 ampere, or it is present at 9 ampere, or it is present at 3 ampere. Okay, so that's the problem. Okay, now on the other hand, we have this emitter, and this emitter is used to detect the alternating current. And here even if we connect the alternating source here, okay, with this emitter here we know that this AC supply, it is changing its polarity and it also changing its magnitude, and due to that here this needle was vibrating. So in this case, in this emitter, this needle is not vibrating. Instead, we connect the AC supply here. Their polarity and magnitude is changing, but here this needle is at fixed position. It is not changing. Such type of the emitter is present in the circuits of your homes. Okay, it give us the specific value that whether the current is this or that. Okay, so in that case, this needle is not vibrating. Even the supply is changing its magnitude and direction. So what is the physics and logic behind that? Okay, so we will answer that in the last portion of this video. So let's take so here we have that AC supply. Okay, it's changing its magnitude. So let's say this is the current. Okay, this is the current, and the y-axis we have current. This is the zero position, and this is the current with the negative sign. Okay, and here let's say this is the zero angle, this is the 90 degree, this is the 180 degree, this is the 270 degree, this is the 360 degree. Okay, so here let's say we have this at zero position, the induced EMF is 0 and hence the current is 0. Let's say this is actually 45 degree, this is the 45 degree, and at 45 degree we have this instantaneous alternating current. At this instant, at 45 degree, we have this alternating current which is about 7 ampere. And here at 90 degree we have this instantaneous alternating current. Okay, we have this instantaneous alternating current, and that is about 10 ampere, and it is the peaks and maximum value of the current in the positive side. And in the same case, for each degree, the change in magnitude of the alternating current is occurring. Okay, so for this degree, for each and every degree, this is decreasing. Okay, and at final at 180 it becomes 0, and this is the 135 degree. At 135 degree we have this instantaneous current which is about 7 ampere. And similarly on the other mirror on the other side, on the other half of this cycle, we have the current with the negative sign, and it is given by the Fleming right hand rule. Okay, and I have discussed this in that alternating current video. Okay, so in this side now the polarity is changing, and now here let's say this is at this position we have the negative sign, minus 7 ampere. This is 7 ampere because this is present in the negative y-axis. Okay, and here this is the maximum alternating current but in the opposite direction, and here this is minus 7 and 360 degree. This value of the alternating current again comes to 0 position. So now taking the average of this alternating current, average is equal to, this is actually I1, this is I2, I3, I4. Okay, in one half circle I consider the 4 instantaneous value, and similarly in this cycle I consider the 4 instantaneous values. Okay, so let's say this is the I1 plus I2. I'm going to take the average, so this is the I2, I3, I4, I5, I6, I7, I8. Okay, this is up to I8, and here I consider the 8 instantaneous values, so therefore we have to divide that with the 8. Okay, so this is the method for defining the average, and here the I1 is the 0 ampere. Okay, so I'm going to put the values of the I1, which is the 0 ampere, plus this is the I2, which is the 7 ampere, I3 with the 10 ampere, I4 with the 7 ampere, I5 with the 0 ampere, I6 with the minus 7 ampere. So this is minus 7 ampere, and this is 1 2 3 4 5 6, and this is the minus 10 ampere, and this is the actually 1 2 3 4 5. Okay, so this is minus 10 ampere, this is the minus 7 ampere, and again this is the plus 0 ampere, and divided by this. Okay, which is 1 2 3 4 5 6 7 8 9. This is actually 9. Okay, so I am going to update this. This is actually I9. Okay, and here we have the 9, and this is actually the average of the alternating current. Okay, so here this 0 is cancelled with the, let's say, this 0, this minus 7 plus 7 plus 7 minus 7 minus 10 plus 10, and it is equal to 0 divided by 9, and everything divided everything which is in division, but in the top we have the 0. The answer will be the 0. Now the average of this alternating current is 0. Okay, because it this half circle. Okay, so here at this fourth portion of this cycle we have that is increasing with the positive signs, and at this portion we have the alternating current is increasing with the negative sign. So this portion and this portion will be cancelled out, and here this portion and this portion will be cancelled out, and the average of the alternating current is always 0, because here is the symmetry is present. The half cycle is in is 1, and the other half cycle is actually the mirror image of that. So therefore the average of the alternating current will be always 0. Okay, so from here we conclude that here if I provide the AC supply, it will be show us, let's say, some deflection. Okay, so here this deflection is not due to the average. Okay, so how then it show a specific deflection with us with a specific value. Okay, so that's not due to the average. Now I'm going to here the average is 0. So what will we do that is that the answer is not become 0? So for that I'm going to take the square of this current. Okay, so if I take the square of this current, this negative sign will also become the positive, and in that case here the I average, let's say this is the I, so for that I am going to the square of these this current. So let's say this is I square, which is equal to I1 square, I2 square, I3 square, I4 square, I5 square, I6 square, I7 square, I8 square, I9 square, I9 square. So this is the I square, and I'm going to put the values here. Okay, which is equal to I1 is equal to 0 ampere. Okay, this is equal to 0 ampere whole square plus I2, which is actually 7 ampere whole square plus 10 ampere whole square plus 7 ampere whole square plus 0 ampere whole square minus plus minus 7 ampere whole square plus minus 10 ampere whole square plus minus 7 ampere whole square plus 0 this is actually the I square values. Okay, so here I square is equal to 0 square. So I'm going to find the values here. 396 ampere square. Okay, so this is the value of I square, 396 ampere square. Okay, this is actually the I square. Now this is the square. Now I'm going to take the average of this average. The average of this current is equal to let's say I average is equal to this I square average is equal to this I square value divided by these are 9 values, so divided by 9, which is equal to 396 ampere square divided by 9. Okay, and it is equal to 44 ampere square. So this is actually the average of that I square. Now I'm going to take again the square root in order to avoid this I square. So for that I'm going to take the square root of I square average is equal to the square root of 44 ampere square. Okay, which is equal to, and we have this value. Okay, now this value is called the root mean square, RMS. So here from this root we take the R, and from this average is also equal to mean. Okay, so from this mean we take M, and from this square we take S. So this is equal to RMS. So this is actually the RMS value, and which is a fixed value. Okay, and this value is actually the 70. This is actually the 70.71% of the I maximum. This 6.63 is actually the 70% of that maximum current, which is 10 ampere. Okay, so here we have the maximum current is I maximum is equal to 10 ampere. Okay, and this is the I root RMS. I RMS is equal to 6.633 ampere. Okay, so this is actually the 70% of this maximum value. Okay, so this here this ammeter, which is the ammeter for the alternating current, will give us the RMS value. Okay, it will determine the RMS value, and here if we have this like sine function, and if we provide that to this alternating current ammeter. Okay, so if we provide this, if this source have 10 ampere amplitude. Okay, so if this wave have 10 ampere amplitude, then here it will show us the 6.633 ampere current. Okay, because it gives us the RMS value, not the maximum value. As you know that this is actually the step down transformer, and we provide the 220 voltage. Okay, the voltage which is present in your home is about 220 volt. Okay, so this 220 volt, this is here is the fixed value, and here this is actually the alternating current. Then how you put here is a fixed value. Okay, so this fixed value is actually the VRMS value. This is actually the VRMS value. This is actually the VRMS value. Okay, this is not the peak value. The peak value will be more than this 220 volt. Okay, and here this step down transformer convert that into 3 volt, that convert into 3 volt, 6 volt, 9 volt, and 12 volt. So this 3 volt is actually the RMS value. This is the RMS value, root mean square value. Okay, this is 70.7% of the maximum voltage. Okay, so if the amplitude of this source is let's say this will be maximum, and this is the RMS value, their amplitude will be more than this value, and here this is also the RMS value. This is the RMS value. Okay, this is not the peak value. So this RMS value is actually the fixed value, and which is here from this diagram. Let's say we have there 220 volt voltage. Okay, so that 220 volt is present. This is actually present here. Okay, this is about the 70.7% of this total ampere, this total amplitude. So the total amplitude is from this 0 position to this position. Okay, and this portion here I label as with the yellow color is the RMS value, and that RMS value we determine by applying these mathematics. Okay, so this 220 volt is not that maximum amplitude, that is actually that RMS value having a specific amplitude, and that the amplitude of the RMS value is about 70.7% of that maximum amplitude. Okay, so this is actually the peak value, and this is the RMS value. Okay, and in this RMS value, let's say if we draw the line on this RMS value. Okay, so if we draw the line on this RMS value, then it will this AC will be converted into, this behavior of the AC will be converted into DC, and here it will behave as a DC current. Okay, so this is the 240 volt. So this is the that 240 volt, which is the RMS value, and here it will behave as a DC voltage, and therefore it we know that in DC voltage this needle will be at specific position, so therefore this needle is not vibrating. Okay, so this is actually the RMS value, and that is behave as a DC voltage. So in your book the RMS value will be defined as the heat which is produced by the DC voltage will be equal to the heat produced by the RMS value of the alternating voltage. Okay, so here the heat produced by that alternating voltage having the RMS value of 240 volt will be equal to the heat produced by the DC voltage with the value is with the voltage is 240 volt. Okay, so this 240 volt of the DC voltage will be equal to the 240 RMS voltage of the AC. Okay, so from where I conclude that this is the 70% of this. Okay, so for that I'm going to perform the calculation further. Okay, so let's say we have the current at any instant is given by this formula, which is equal to I instantaneous. I instantaneous is equal to I maximum maximum into sine theta. I maximum into sine theta, and here we know that this sine theta, this theta is equal to omega t, so we can write this as a I instantaneous is equal to I maximum sine omega t. Sine omega t. It means that at any instant, if I am interested to find the instantaneous value, so let's say at 45 instant, the instantaneous value is given by this. So I instantaneous is equal to I max into sine theta. Here the I max, the maximum current in this case is 10 ampere. So instead of this I max, I will put the 10 ampere and into sine and theta. So at which instant, at which angle you are interested to find the instantaneous value, you will fit that here. So this is about 45. I'm interested to find the instantaneous value at 45 degrees. So here I'm going to put that 45 degree. Okay, so it will become it will give us the scalar value, and that will be the instantaneous value. So for each and every instant, so for each degree rise on the x-axis, you can find the instantaneous value if you have the maximum, if you know the maximum amplitude or the maximum current. Okay, so this is the this is actually the what we can say the formula for finding the instantaneous current, and similar formula is used for finding the instantaneous voltage, which is equal to the maximum voltage maximum into sine theta or sine omega t. Okay, so here I have written that I instantaneous is equal to I max sine theta, and instead of this theta I put omega t. Okay, and from let's say we consider the resistor and the power delivered to resistor. The power delivered to resistor is given by P is equal to I square. P is equal to I square into R. So this is actually the instantaneous value. Okay, so here I'm going to put the values. So I instantaneous square, so this is actually the value of the I instantaneous, which is equal to I max. Okay, this is equal to I max sine omega t, and here this is the square, so we'll put square on the top of that, and this then multiply with the R, and here the power is equal to I max square square into sine omega t whole square. So sine square omega t sine square omega t into R. So this is sine square omega t into R. This is the relation for the power delivered by resistor, which is connected with the AC supply. So let's say this is the equation 1. Now actually we are interested in the RMS value. So the power for the RMS current, root mean square current, is given by P is equal to P RMS is equal to I RMS whole square, okay, into R. Okay, let's say this is I RMS whole square into R, and this is the equation 2. And here compare the equation 1 and 2. The left side of these equation are same, so compare equation 1 and 2. The left side of these equations are the same, so their right side will also become equal. Okay, so the right side of this equation 1 is the I max, let's say this is the I maximum whole square into sine square omega t into R, which is equal to this I square RMS into R. Here this R and this R will be cancelled, and it will give us this value. Okay, so on the left side we have I max whole square into sine square omega t sine square omega t, okay, which is equal to I square RMS. So here I sine square omega t, so let's say this is equal to the I max whole square is equal to sine square theta. We know that omega t is equal to theta, so it is equal to I square RMS. So this, the value of the sine theta is the value of the sine theta is from the 0 to 1. It do not exceed the 1. So the average of this is actually this. Okay, the average of this is actually the average of so the sine square is equal to 0 square plus 1 square. Okay, and its average is equal to this. So these are two values, so therefore we divide that by 2, so this is equal to 1 by 2. Here instead of this sine square theta, I will put this one word 2. Okay, so that this value will become I square of I max square. Instead of this sine square of theta, I will put one word 2, and which is equal to I RMS whole square. So I am interesting in the I RMS. Okay, so for that I am going to take the square root again on the both sides. So this is the square root, and here we have the square root on this side as well. Okay, so this become this square root with the I max will be cancelled. Okay, this square and square root will be cancelled, and here divided by square root of 2, which is equal to this square, and this that will be cancelled, which is equal to I RMS. And this is the final equation for the I RMS. So this is actually the final equation for the I RMS, and which is this I RMS is equal to I max okay, divided by square root of 2, and the value of here the value of this 1 over square root of 2 is this. So I RMS is equal to, instead of 1 over square root of 2, we will put 0, let's say that is 0.7071 into I max. Okay, so 1 over square root of 2 is equal to this value. So the I RMS, so in percentage we can write here is that I RMS is equal to 70.71% of I maxima of I maximum. Okay, so this, from this relation, here according to this relation, the RMS value will be the 70.7% of the I maximum value. So here we had find the RMS value, which is 6.33, which is actually the 70.7% of the I maximum, and the I maximum is 10 ampere. Okay, so the 70.7 of this 10 ampere is actually this up to here. Okay, and this is actually the I RMS, and which is equal to about from here, which is equal to 6.633 6.633 ampere. Okay, this is the I RMS value. So from all this discussion, I'm going to conclude that here if we provide the AC source to the galvanometer, okay, it will the needle of this galvanometer will be vibrating. So for that we have to consider a single value in the alternating current, that this needle will be at fixed position. Okay, so here we have that ammeter for the alternating current, and for that we need a specific single value. Okay, so that is not possible for the AC supply. So for that we apply the mathematics, and from that mathematics we conclude that we will have to take the 70.71 percent of the maximum value. Okay, and that will be shown on the AC ammeter. So here it show the deflection. That deflection will be actually 70.71% of the maximum value. So let's say we have in our home the AC supply, the voltage is about 240 volt. Okay, so this is actually the RMS value. This is not the peak value. The peak value will be more than that. This RMS value will be the 70.7%. Okay, so at that position, at that specific instant, the alternating voltage will be considered, and here this needle will be deflected, will be present at only that instantaneous alternating current or alternating voltage. It will not vibrating. Okay, so at that instant the RMS value is given by this, and now this is behave as a DC current. So therefore DC current or DC alternating voltage. So therefore we convert that not the whole AC current, but at a specific instant, if we consider a specific single instant of the alternating current or voltage, that will be behave as a DC current or the DC voltage. So therefore, for that specific instant, we have to draw the line which is same in magnitude throughout. So at this time, that is so at this zero time, the voltage is 240 volt, and similarly at this position the voltage is also that 240 volt. So at this time the voltage is that same 240 volt, and at this time that voltage is same 240 volt. So therefore, by changing the time, this will be the same, this deflection will be the same, that will not changing, okay, by changing the time.